All right, so this is the Young double slit experiment in class lecture problem. We have two speakers. Now, the Young double slit experiment was done with light, but would this also work with sound?
Yeah.
Yeah, because sound is also wave-like, so it's the exact same concept. So what we have here are two speakers, and notice in the problem it tells us that in the second sentence that the sound waves from the speakers are in phase with each other. So what does in phase mean? The sound coming from this upper speaker is like this. Peak starts out like that, right? The sound from the bottom speaker is the exact same thing. They are starting out in phase. That's the only way that the double slit experiment is going to work. Okay, now, here's what happens. This upper speaker, so I'm going to show the sound waves like this as wave fronts. So it's giving off these wave fronts like this, right? And these wave fronts are moving towards this, well, not a screen, but like where we have a sound sensor over here. The pattern here is going to be loud, quiet, loud, quiet, loud, quiet, as opposed to bright, dark, bright, dark, bright, dark. The easiest way to say that would be minimum, maximum, right? And then this lower speaker here is also emitting wave fronts like that. And then what happens is the places where the waves are in phase, like there, and then, oops, this should be constructive. Nah, it didn't really work out. This should be constructive all the way across. Like the constructive points are like this, right? Like that. You know, this is where you have constructive interference, and then you follow this out like this, and then that's going to lead to what? Loud or quiet?
Loud.
Loud. Like where you have constructive, it's loud. Now, my diagram was drawn very poorly here, but just so you know, you should have, if you do this nicely, you draw these wave fronts very carefully, you should have constructive all the way across the middle. Constructive, 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 where the wave peaks are overlapping, and then you're going to get a loud right in the center. All right? So that's kind of the setup of what's happening. The equations that apply here are this. You're going to say d sine theta, d sine theta equals m lambda. Now, for small angles, so if you're focusing on a point right here, your theta is going to be the angle from the center line. This is your theta, but theta is also going to be, if you're comparing two rays that are traveling from these speakers, theta also appears in this little triangle right here. This is theta inside there, right? So the extra distance traveled is that. That works out to be d sine theta. And to get constructive, for this to be a loud point, the extra distance traveled by this bottom ray, this distance right here, has to be equal to a whole number multiple of the wavelength. Now, sine theta are small angle approximation, so we're going to call this distance here y, and then L is this. So for small angles, we can say sine theta equals y over L. You take this, plug it in up there, and that's going to give us y equals lambda L over d times m. So we're going to be using this equation. Okay, so going through the worksheet. Question A, calculate the wavelength of these sound waves. So to do question A, all we need is velocity equals wavelength times frequency. So wavelength is velocity over frequency. The speed of sound is given as 343 in the problem. And then the wavelength is, that's what we're solving for. The frequency is given as 2,500 hertz. So then, what's the answer here? 0.14. So we got the wavelength like that. Now, question B. The student moves. Okay, so you know what? I got to totally redo this. Set this up again. Speaker, speaker, over here. Here is point P, here is point Q. So the student moves a distance y to point Q, like this. And notices that the sound intensity has decreased to a minimum, so this is going to be quiet. calculate the shortest distance the student could have moved to hear this minimum. Okay, so what's M going to be equal to? So the pattern looks like this. So in the middle, it's going to be nice and loud, right? Nice and loud. Oop, let me redraw this. So this is going to be quiet here. So it's going to be boom, boom. So you got this loud region right in the middle. Okay? So what's the M value going to be here? M equals 0, right? You have M equals 0 on both sides of M equals 0. So this is M equals 0 for constructive interference. This is M equals 0 for destructive interference. Okay, so we're looking at the sound waves that are traveling boom to boom. So the top ray is traveling farther, right? So what's this d sine theta going to be equal to? D sine theta is going to equal, so if it's destructive, you're going to say m plus 1/2 lambda, where m is 0. So basically this extra distance traveled is going to be half a wavelength. Okay? So we go d sine theta, it's m equals 0, so that's going to equal wavelength over 2. But now what can we plug in for sine theta? If it's a small angle, well, theta is also from the midpoint between the speakers down to there. Theta is also this right here. So what could we say about sine theta? It's going to be opposite, which is y, and then we're going to approximate the hypotenuse to be what? L. And L is this distance right here. That's L. So we approximate that. Sine theta equals y over L. Plug that in, so we get dy over L equals lambda over 2. So what's y going to equal? Y is going to equal 2 dy over L. So the distance between the speakers is 0.75 meters. Y is, oh wait, what did I do?
You mean lambda.
Lambda. Wait, hold on, I messed up.
No, you
Y
just
equals,
change 2dy to 2d lambda.
yeah, this should be 2d lambda. Okay, and then this is 0.14, and then L is 5 meters. So you plug this in, and what's the answer?
D should be on the bottom.
0.46 meters. Let's see, let's check my algebra. dy over L. So y should equal
Shouldn't L be on top?
L lambda.
Lambda L over 2D.
Yeah, lambda L over 2d. Dude, I totally messed this up. So in this algebra, darn it, L lambda over 2d. I just made an algebra error. So let's fix this. So it comes out as 0.46. So L is 5, lambda is 0.14, 2, and then the distance between the speakers is 0.75. And you get 0.46 meters. Okay. Identify another location on the line that passes through P and Q. Where is another location where the student could stand in order to observe a minimum? Well, look, what you could do is you could change the order number. So go and find, so this pattern continues, right? It's going to go loud again and then quiet. Now look, if you wanted to find out where this minimum was, so going back here, so this is d sine theta equals, so the original equation was d sine theta equals m plus 1/2 lambda. So our first calculation had m as 0. So now let's make m equal to 1. So now this would be 1.5 lambda. So all you got to do is you got to come in here and make this 1.5 lambda right there. So how does that change this calculation? So y is going to equal 1.5 L lambda over 2d.
Is it okay if we did -1?
Wait, hold on. No, that 1/2 is gone. That's gone. So this will be 1. This is 1.5 lambda, so take that 2 away. So instead of 1/2, it's going to be 3/2. Yo.
We did -1/2.
Well, technically, this is negative down here. If you're dropping below the center line, that is negative. But another acceptable answer would be another spot where you would have a quiet. The easiest answer would just be come up here. Go up there, and then that's going to be the same thing. That's going to be 0.46 meters measured off this center line right here. That'd be the easiest way.
So do we have to show the first one as being negative and the second one as positive?
You would just specify above or below the central maximum. So you say like this one is 0.46 meters below the central maximum, and then this one up here is 0.46 meters above the central maximum. All right, now last part. How would your answer to part B change if the two speakers were moved closer together? So to answer this, look at our equation is this. Y equals lambda L over D m plus 1/2. That's pretty much the equation. So we get this pattern of loud in the middle, and then it gets quieter like that. This is our pattern. So the speakers are over here like this. So look, how would your answer to B change if the two speakers were moved closer together? Well, what's D here? D is, it's the distance between the speakers. So look at our equation that we derived right here. If D becomes smaller, what's going to happen to Y? It's going to get bigger. So what happens is this interference pattern spreads out. So instead of looking like this, it's going to look more like, it's going to be like, try it again. It's going to spread out like that. Does that make sense?
So as D gets bigger?
As D gets smaller, because what the first thing, it says, how would your answer to B change if the two speakers were moved closer together? If you're moving these two speakers closer together, what's happening to D? It's getting smaller. If D gets smaller, Y gets larger. Okay, next one and last one. How would your answer to B change if the frequency emitted by the two speakers was increased?
So that means they're faster.
Well,
part of this.
The frequency? Well, look. It's a trick question. You look at this equation, does frequency appear anywhere in here? No. So how are we going to get frequency into this? Well, remember, velocity equals wavelength times frequency. What do you know about the speed of a wave? It's constant for a given medium. The velocity is constant for a given medium. So if the velocity is staying constant and they tell us that the frequency is increased, if you're increasing the frequency, what must happen to the wavelength? The wavelength must decrease. Now look at this equation up here. If the wavelength is decreasing, if the wavelength decreases, what must happen to Y? It must decrease. So the answer is the interference pattern is going to smush together, right? Instead of looking like this, it's now going to be something like everything's going to get closer together, right? So instead of being that far apart, it's going to be closer.